Hello everyone, I hope you're doing well today. What we want to talk about is inverse trigonometric functions. Now, if you've taken a trigonometry class, and I hope you have, then inverse trig functions are defined and practiced quite a bit in a trigonometry course. But in case you're having trouble with that, please watch the videos from my trigonometry course covering inverse trig functions. One thing that's covered in that is the development of these inverse trig functions and the domain and range. So I'm going to briefly review this, but again, if you're struggling with any of this information, go back and watch those videos on the development of inverse trig functions and how to work with them and many examples of problems using inverse trig functions. And notice there are 6 defined right here. The first one being y equals arc sine. Now, you could write that as y is equal to inverse sine of x is identical as arc sine. So some books use those terms interchangeably. This book I notice uses arc sine, arc cosine, arc tangent rather than inverse sine, inverse cosine, and inverse tangent. But those are identical functions. Now, it says y equals arc sine of x or inverse sine of x if and only if sine of y equals x. The domain is -1 to 1. So you cannot plug in any value into an arc sine or an inverse sine because those are the same functions if it's outside of this domain. Like you cannot evaluate the arc sine of 2 or the arc sine of -5 because it's not between -1 and 1. Now the answers, in other words, the range for arc sine or inverse sine is between -pi/2 and +pi/2. If you think in terms of the unit circle, it is only this half of the circle. Okay? Now arc cosine, another way to write that is y is equal to the inverse cosine of x. They are the same function, this function and this function. Notice once again the domain is between -1 and 1, so you cannot evaluate the arc cosine of 4 because it's outside of this domain. But notice the answers, the range is between 0 and pi. So if you think about that in terms of the unit circle, you're only talking about the top half of the function. Okay, now arc tangent, the domain is between -infinity and infinity. So you can plug in any value you would like into the arc tangent or the inverse tangent. Again, another way to write that is like this. Okay, but the domain is very similar to the domain of inverse sine. It is only the right half of the unit circle, -pi/2 to +pi/2. But notice it's not equal to, because tangent of those values gives you undefined, therefore there's no equal to here and here. Okay, now what I didn't define in those videos from the trig class would be arc cotangent, arc secant, and arc cosecant. The reason is these are the reciprocals of these. So in my mind and in most trig books, thought is that if you can work with arc sine, arc cosine, and arc tangent, that would handle all of your needs. You wouldn't necessarily need an arc cotangent, an arc secant, and an arc cosecant. But this calculus book defines all those as well. So arc cotangent, very similar to arc tangent, your domain is -infinity to infinity. You can plug in anything you want, but the range needs to be between 0 and pi, just like arc cosine. Okay, arc secant, you can only plug in values bigger than 1 or less than -1. That's what the absolute value is greater than or equal to 1 means, so less than -1 would apply. And then the range is between 0 and pi, but you cannot include pi/2. And arc cosecant, once again, if you think about the graph for arc secant and arc cosecant, this makes really good sense because the range turns into the domain and the domain turns into the range for those values. And that's why when you look at the graph, say for arc cosecant, there's nothing graphed between -1 and 1, so there's your range and goes back to your domain. Now the range for arc cosecant would be negative pi over 2 to pi over 2 as long as y is not equal to 0, which is similar to the y is not equal to pi over 2. Now again, the development of that would probably make more sense if you went back and watched the videos. I just want you to have a working knowledge of this. I'm going to make this video short and not re-explain all those definitions. It does make a remark here that's pretty important. The term arc sine of x is read as the arc sine of x, or sometimes the angle whose sine is x. And again, you're just thinking backwards. So for example, if I gave you, say, the arc sine of square root of 2 over 2, I'm asking you the sine of what angle is equal to square root of 2 over 2. Now, if you're thinking about the unit circle, that happens in two different places. It happens here and it happens here. If you know the unit circle well, you know that's pi over 4. And this guy down here is 5 pi over 4. But remember, for arc sine, our answers need to be between negative pi over 2 and positive pi over 2. So that is the answer, pi over 4. Okay? So you're just asking what angle gives you that result. So to just make sure we're comfortable with this process, and again, this is supposed to be a review, so if you're struggling, go back to the videos that I have listed from a trigonometry class that explain inverse trig functions in extreme detail. But just throw out a couple of problems. Arc sine of theta. Now, y'all, this problem is no different than saying the inverse sine, not of theta, of 0. Goodness, what's going on with me? So there we go. The inverse sine of 0, this is the same problem. And what you're really asking yourself is sine of what angle equals 0. Now, again, you either need to know your special triangles or your unit circle, but sine of 0 equals 0 and sine of pi equals 0 on the unit circle. Because remember, you have a unit circle and sine is the y values. So y is equal to 0 right there, and y is equal to 0 right there. But inverse sine or arc sine is only defined between negative pi over 2 and positive pi over 2. So this answer of pi over here is out. The only answer that applies would be 0. So the arc sine of 0 is 0. So let's think about this again. How about arc cosine of 1? That's no different than saying inverse cosine of 1. And what you're asking yourself is cosine of what angle equals 1. Now, on the unit circle, cosine is an x value. X is equal to 1 right here and nowhere else on the unit circle. What angle is that? That would be theta. The angle theta equals 0. So the answer to this is 0. Happens to be the same location as the problem above. And then arc cotangent equals negative square root of 3. Again, another way to say that is inverse cotangent of negative square root of 3. So you're asking yourself cotangent of what angle is equal to negative square root of 3. Now that's a little tougher to think about. Cotangent, if you'll recall, is cosine on top, sine on the bottom. If you're thinking about that term in terms of unit circle, that's an x value over a y value. So I'm asking myself, what combinations of numbers would give me negative square root of 3? Okay, well, how about if I have square root of 3 over 2 in the top and say 1/2 in the denominator? Now, if you invert and multiply, you notice that will give you square root of 3. The 2's will cancel out, but how do you get the negative? Now, the negative could be in the numerator or, not both, in the denominator. Now, where does that happen? That x is equal to the square root of 3 over 2 and y is equal to 1/2. Well, on our unit circle, how about this angle right here? If you go look at a unit circle, x is equal to square root of 3 over 2, y is equal to 1/2. Where else could that happen? Right over here. X is equal to negative square root of 3 over 2. Y is equal to negative 1/2. Well, look, that's not going to do it for us, right? Those are both positive. Those are both negative. How about this one? In this case, x is negative square root of 3 over 2. Y is positive 1/2. That would do it, right? And this one, x is positive square root of 3 over 2, and y is negative 1/2. So we know it's either this angle, by the way, that's what, 5 pi over 6? And this angle down here, 11 pi over 6. Or negative pi over 6. So it's either this one or this one. But maybe we need to know what the range of arc cotangent is. And this is when you can refer to our chart here. And the range of arc cotangent is between 0 and pi. So if I go back to my problem, the only result between 0 and pi is this 5 pi over 6 result. So my answer is 5 pi over 6. So that's how you just evaluate. All you're doing there is evaluating inverse trig functions. Now here's some more properties of inverse trigonometric functions that you need to know. This is also covered in my trigonometry videos on inverse trig functions. But notice the sine and the arc sine here. We can say that those will cancel out as long as your x value is between -1 and 1 and your y value is between negative pi over 2 and pi over 2. So once again, those cancel out as long as that's the case. If that's not the case, you would have to see if you can first of all even evaluate what's inside here and then take the sine of it. But here especially, if you take the sine of y, you can take the sine of any angle because the domain of sine is all real numbers. But if this y is not between negative pi over 2 and positive pi over 2, you would first evaluate the sine of that and then calculate the arc sine of your answer. But it won't be the same y value that's right here. Okay, so just wanted to point that out because that is very important as far as evaluating trig functions. Now, a problem that shows up frequently, especially in a calculus class, is write the expression in algebraic form. And notice this doesn't fit any of the guidelines we have here, because notice this is sine and arc sine, this is tangent, arc tangent, secant, arc secant, and the opposite here. So these are inverses of each other. So tangent and arc tangent should cancel each other out as long as these conditions are met. But the secant and arc tangent are not inverses of each other. So to write this expression in algebraic form, the best thing to do is to draw a triangle. Okay, so I'm going to draw a right triangle, because all of the trig functions are defined on a right triangle. And I'm going to go with the inside first. I'm just going to write down what that is actually saying. It's saying arc tangent of 4x. In other words, tangent of some angle, I'm just going to call it theta, is equal to 4x. Now, tangent by definition, in terms of triangles, y'all know that is opposite over adjacent. Right? So if I make this algebraic expression into a fraction, I'd put it over 1, which means 4x is the opposite side, 1 is the adjacent side. So all of you know, when you have a right triangle, you can label your trig function values here. And now opposite and adjacent depends on what angle we're talking about. So certainly we're not talking about the right angle. So you either have to pick this angle or this angle, and I always pick the one here if I have an option. So there's theta. So now I can define opposite. Opposite of theta is this side, the vertical side over here, and I'm going to label that as 4x. Whereas adjacent to the angle theta is 1. Now we can find this missing side by using the Pythagorean theorem. So I can say side squared, which is 1 squared, plus this side over here squared, which is 4x all squared, is equal to the hypotenuse squared. Or you can call it a variable if you want. So 1 squared is 1, 4x squared all squared is 16x squared is equal to the hypotenuse squared. If I solve for the hypotenuse, I would need to take the square root of both sides. So the hypotenuse, we know, is the square root of 1 plus 16x squared. So now all my sides are labeled. Notice I did all that from just the inside. Now I'm ready to evaluate the secant of theta, because we called that angle theta. So secant, we know secant is 1 over the cosine is how I remember that, and we know cosine is adjacent over hypotenuse. So secant of theta is hypotenuse over adjacent. Sorry about the battery thing, y'all. I think I've got it straightened out now. So anyway, we've got secant of theta is hypotenuse over adjacent, and the hypotenuse side, looking at our triangle, remember that's the angle across, or the side across from our angle. So it's 4x, okay, divided by the adjacent side, which is 1. Oh, goodness gracious. It's not 4x. The hypotenuse, y'all saw that, it's the square root of 1 plus 16x squared. Let's try that again, and the adjacent really is 1. So the answer to this problem, the secant of arctangent of 4x, is the square root of 1 plus 16x squared. Okay, so you see that. So here's the idea. We're going to do another one too, but here's the idea. Start with the inside function first, okay? That's going to be your inverse trig function. You draw a right triangle, pick an angle for theta that's not your right triangle, not your right angle. And, of course, this is the opposite side, this is the adjacent, and the one across from the 90 degrees are opposite. Now, we know tangent is defined to be opposite over adjacent. So that's why I said opposite over adjacent. So 4x over 1. And then I found the missing side using the Pythagorean theorem. That's what all of this was. Then I went with the outside. So secant of, we call that angle theta, by definition, is hypotenuse over adjacent. And the hypotenuse, that's the one I tried to put down wrong, is the square root of 1 plus 16x squared. And the adjacent is 1. And that is my answer, but simplified, we've got the square root of 1 plus 16x squared. Let's try it again. When I go to this next problem, why don't you pause it, work it out, and see if we don't get the same result. All right, so you're ready to try another one of these? We've got the cosine of arc cotangent of x. So again, my advice is to pause it and see how you do with this. Remember to start on the inside, draw your triangle, label your sides, and then evaluate the cosine of what you got. So how'd it go? So here's my triangle. I know I've got to do that. There's my 90 degrees. Now at this point you have to pick an angle for theta. I'm just going to call it this one. And then I'm going to start on the inside. So what this is saying right here is that cotangent of, we called it theta, is equal to x. And we need to write that as a fraction, x over 1. Now we know cotangent is adjacent over opposite. You know, that is the definition of cotangent in terms of sides of a right triangle. So the adjacent side corresponds with the x, so that's x, and the opposite side corresponds with the 1, so opposite of theta over here is 1. What we need to find is the hypotenuse. So we use the Pythagorean theorem, so x squared plus 1 squared is equal to the hypotenuse squared. So that's x squared plus 1 is equal to the hypotenuse squared. I solve by taking the square root of both sides. Now, algebraically, you know when you take the square root of both sides, you're supposed to put plus or minus. But we're talking about the length of the side of a triangle in this case that's not inside the xy axis. Therefore, we're just talking about x squared plus 1 over here. Now we're going to say the cosine, working on the outside trig function now, the cosine of theta is equal to, now we know cosine is adjacent over hypotenuse. Correct? Just by definition. Adjacent side is x. The hypotenuse side is what we solved for, the square root of x squared plus 1, and that is your result. So cosine of arc cotangent of x is equal to x over the square root of x squared plus 1. Okay, folks, so now the meaty part. We want to take derivatives of these functions. Now, trigonometric functions like natural log or logarithmic functions and exponential functions are called transcendental functions. They're not algebraic, but look, the derivatives are. Okay, so when you take the derivative of arc sine, believe it or not, you get an algebraic function. Notice, no matter what's in here, that's your u. This is like the chain rule. And your answer is going to be the derivative of u, so the derivative of the inside of your arc or your inverse trig function over the square root of 1 minus the argument inside the trig function squared. So that's arc sine, whereas arc tangent, again, the derivative is the derivative of your argument of arctangent or inverse tangent over 1 plus that argument squared. And then arc secant, again, is the derivative in the numerator of the inside of your inverse function over the absolute value of the inside of your inverse function times the square root of that inside squared minus 1. Now the good news possibly for you is that you might not have to have these memorized when you do these problems, but with enough practice they aren't bad to memorize. Okay, so if you're able to use a formula, good for you. If you're not, then definitely do plenty of these problems so that you will have these formulas memorized. And notice that what else is the difference? The derivative of inverse sine is positive, whereas the derivative of inverse cosine is negative. The derivative of inverse tangent is positive, where inverse cotangent is the same formula but negative. Same thing with inverse secant is positive, inverse cosecant is negative. So let's try some of these problems. And here is the first one on the list, the derivative of arc sine of t squared. Now, my advice is to write the formula down. So the derivative for arc sine is that first one listed, u primed over the square root of 1 minus u squared. So here we go, u primed, let me write it, u primed over the square root of 1 minus u squared. Now what's u in my problem? Well, u is t squared. So if I use my formula, u primed, that's the derivative of u, is 2t over the square root of 1 minus u. Okay, so u squared is t squared, but it's got to be squared because it's in the formula. So simplified, by the way, that would be f prime of x, right? So simplified, that's 2t over the square root of 1 minus t to the fourth. And there's your derivative. So next let's supposed to find the derivative of arc secant of 2x. Now keep in mind, the same problem could look identical to this. So the inverse secant of 2x. That's the same function, just different notation. But no matter, I need to look up the formula. Okay, so to take the derivative of arc secant or inverse secant, where's our formula? It's right here, right? Okay, so it's u primed over the absolute value of u times the square root of u squared minus 1. So let's write that down first. So it's u primed over the absolute value of u of the square root of u squared minus 1. Now u in our problem is 2x. Okay, so when I plug it into the formula, f prime of x is equal to, numerator is u prime, the derivative of u is 2 over the absolute value of 2x times the square root of u squared, so that's 2x squared minus 1, simplified, is 2 over the absolute value of 2x, not simplified yet, the square root of 4x squared minus 1. And here's what I notice. Look, this 2 and this 2 will cancel. Can I do that? Absolutely, because 2 is positive, so I could rewrite this as 2 times the absolute value of x, and see it cancels. So I have 1 over the absolute value of x, it can't come out, over the square root of 4x squared minus 1, and there is your derivative. Not bad, right? Especially if you have the formulas in front of you. And if you have to memorize them, just do enough problems, it'll stick. So our next problem, arc tangent of the square root of x. So we need the formula. So let's go back and look at the formula. So here they are. Now arc tangent is the second one here, u primed over 1 plus u squared. So f primed of x, general formula is u primed over 1 plus u squared. So what's u in our problem? Well, u is the square root of x. So u primed, I can go ahead and write it right here, you know, think about that as x to the 1/2, so it'd be 1/2 x to the negative 1/2. When I plug that in my formula, I have f prime of x is 1/2 x to the negative 1/2 divided by 1 plus u squared. So that's going to be the square root of x squared. All right, now I could rewrite this. This is going to be 1 over, now that 2 I'm going to take to the denominators. I'm going to take the x to the negative 1/2 down there too, so that's the square root of x times 1 plus x, because this square root and that square cancel. Now you got to be a little bit careful. When you take the square root of x squared, y'all, that's really the absolute value of x. But here's what I want you to notice. U originally was the square root of x, so you cannot plug in negative numbers into a square root. So I don't have to worry about the absolute value in this case because x couldn't be negative anyway. It wasn't in the domain of the square root of x to deal with. So this is our final derivative. Okay, next problem. Now, we use that formula again for arc tangent. So the derivative of arc tangent, remember, is u primed over 1 plus u squared. That is just my formula. Okay, now, for this problem, we're going to have to use the product rule. So f primed of x, remember the product rule because we're multiplying x squared times arc tangent of 5x. So I'm going to say first times the derivative of the second. So the derivative of the second is where I use the formula. So u prime is the derivative of the inside, which is 5, over 1 plus u squared, so that's 5x squared. So it's first derivative of the second plus the second, so that's just arc tangent of 5x. I like to put parentheses around my argument, times the derivative of the first, which is 2x. Now it's just about simplifying. So my first fraction is 5x squared over 1 plus 5x squared. Oh, 25x squared, excuse me. I got to square both of those, right? So that's 25x squared. Plus, I'm going to put that 2x in front of the arc tangent, because remember how we like to put trig functions in the back of a product? And y'all, that's about as simple as that gets. It's not pretty, but I don't see the point in finding a common denominator and adding it together. And let's do one more derivative problem. Why don't you go ahead and pause this one and see what you can do with it. Notice you're just adding two separate functions together. So when you take the derivative, you're going to be taking the derivative of that one and the derivative of that one, and then adding the results together. All right, so hopefully you've already done that. So the derivative of arc sine, you might want to look that up. Notice arc sine is u primed over the square root of 1 minus u squared, and arc cosine is the negative u primed over the square root of 1 minus u squared. So the derivative, the inside's x, right? So that's just 1. The derivative of x is 1 over the square root of 1 minus u squared, which is x squared. And then plus, now the derivative of arc cosine is just the negative version of that. So negative 1 over the square root of 1 minus x squared. Wait a minute. Is that not 0? Is that right? What do you think? It turns out it's exactly right. We haven't talked about inverse trig functions a huge amount, but it turns out inverse sine of x, or arc sine of x plus arc cosine of x, is equal to pi over 2, a constant, and the derivative of a constant is 0. So this works out fine, but the good news is we didn't have to know that to do this problem. We just took the derivative of each of them separately using the sum difference rule, and then we realized it's opposite expressions, and when we add them together, you just get 0. It just seems like a weird thing to do, but it is exactly right. And that's the last example I had for you. Hopefully you won't have any trouble taking these derivatives of inverse trig functions, but please let me know if you do. Then you get to come back for one more section, which is going to be the integrals of these inverse trig functions, or at least the answers are inverse trig functions. I hope you have a wonderful day.